And if you have any questions, you can either email Prof. Su Haibing or myself. My email will be given at the last slide. So this experiment is called the electrical characterization of PN junction diode and this bipolar junction transistor. And this is, I would say, based on the course MS 2008. And I hope everyone has learned that. So the objective of this experiment is firstly understand the diode, how does it work, and then characterize the rectification circuit which is based on the diode, and then investigate the transistor characteristic as an amplifier, current amplifier. So as an introduction, first I'm sure that all of us have known there is a material called insulator and another material called metal. So the difference between these two is that there is a huge energy gap in between the valence band and conductive band in this insulator. And this gap is so huge that few electrons can jump over and become free. So which means the conductivity here is very low. While for the metal, it is quite opposite. Because there's no gap here. Instead, there's an overlapping region of conduction and valence band, which means that electrons can easily go from valence band to conduction band and become free. So which means in this case, the conductance is very high. And another difference is that in metals, the resistance actually increases with increasing temperature, which means the conductivity decreases with increasing temperature. This is because when the temperature goes high, the scattering effect and other effects that stop the movement of the electrons that increase. So which means the conductivity will decrease. But however, these two are not ideal materials for electronic applications. The material that we are looking at is called a semiconductor. It does have an energy gap, but it's much smaller than the one in insulator. In this case, some electrons can jump over as long as they get enough energy. And the difference between semiconductor and metal is that at low temperature, the conductance is low, while the temperature increases, the conductance increases instead of decrease. This is because when the temperature goes up, more electrons can gain enough energy to jump over the gap and become free. And which means the conductance change with temperature is opposite in semiconductor and metal. So for semiconductor, we have two types. The first one is the elemental semiconductor, which is the group 4 elements, including silicon and germanium. While for compound is group 3 plus group 5. Like we have gas arsenate, gallium arsenate, and this. So the properties of pure semiconductor, also we call the intrinsic semiconductor, is that all the atoms here are covalently bonded, and it is considered as an insulator at low temperatures. And as we said, that the temperature increases, the conductance increases as well. However, if the temperature goes over high, there will be a bond breaking, which means the bond will be broken here. In this case, the conduction is minimized because electrons cannot travel free within the whole material. It's stuck in this atom. So the conductivity of this material is sensitive to a few factors. First one, temperature, then the illumination, magnetic field, and the last but not least, the amount of impurities. However, in the environment of electronic applications, the temperature, illumination, and the magnetic field are kind of constant. We're not supposed to change them. So the only way that we can tune the conductivity of this material is by tuning the amount of impurities. is this technology we call the doping. So the doped semiconductor, we have N-type doped and we have P-type doped. So for N-type doped semiconductor, it's doped with the group 5 elements, which means once there is a replacement here, there will be an extra electron, free electron, which can be used as a carrier. So the majority carrier in this N-type semiconductor is the electron. But for P-type, it's opposite. Once there's a replacement, there will be an extra hole, which means one electron is missing. In this case, the majority carrier is the hole. So for applications of semiconductor, we have this PN junction diode, which can be used as a switch and can be used as a rectification circuit. And based on that, we have this bipolar junction transistor, which is actually two PN junction connecting to each other, like PNP or NPN, which we will talk about later. And the last one is CMOS, complementary metal oxide semiconductor. This is the key part of all the electronic products currently. So for PN junction diode, if you remember the content from MS 2008, we have this N-type and P-type semiconductor contacting each other. There's a boundary which electrons and holes can diffuse through the boundary. And since there's some extra holes in P-type and extra electrons in N-type, so the carriers, the free carriers will cross over the boundary and combine with the opposite carrier. So in this case, there will be a region called the depletion zone. It is called the depletion zone because in this area, there is very few free carriers as compared to the bulk here and there. And the existence of this depletion zone is to establish an electrical barrier that prevents further diffusion from P-type or N-type, like we said here. In this case, we call it a thermal equilibrium condition. And this is how PN junction diode looks like. You will have a look then at the real part. And remember that in the circuit, the diode goes from anode to cathode. And the cathode here is indicated by a blue tape here, stripe here. And the PN junction, the operation is actually different from the thermal equilibrium condition. In the operation mode, we will have either a forward bias or reverse bias. A forward bias is that the positive side of the positive end of the battery is connected to P-type and negative end to the N-type. This is by doing this, we can see that the electrons will be attracted by the extra by the presence of this positive end, and then vice versa, the holes will be attracted here. So in this case, we can say that the boundary here is lowered. The diffusion zone is kind of shrink, which means diffusion can continue. Well, in the other case, where it is the reverse bias is presented, it is opposite. The holes in the bulk will be attracted this way and vice versa. So in this case, the depletion zone is kind of enlarged, and the barrier is even higher. So in this case, there's no current, as in the thermal equilibrium condition. And this is how the IV curve looks like. As we can see, for the forward bias region, the current goes exponentially with the current, which is the applied bias voltage. Well, if it is a reverse bias case, the current stays like negligible, but not exactly zero. And if the current goes too high, if the voltage goes too high, it's the same as the over high temperature, there will be a breakdown region here, what we call the reverse breakdown region. The current will increase exponentially. However, the direction is opposite to forward bias case. This means that the barrier is kind of a breakdown. There's no barrier there. And this is the region that we never want to see. So we have to make sure that we are staying in this region. And we have this equation here, which I is the current of the diode, which equals to I0 over this, where E and epsilon and K and T are kind of consistent in a certain environment. Well, VD is the only parameter that is changing, which is the applied bias voltage, and I0 is what we call the saturation current. And since the saturation current is kind of negligible as compared to forward bias region, so it can be simplified as I equals to I0 over times this. However, this is an exponential function which is kind of very difficult to understand and very difficult to plot. So we simplify it as we take ln on both sides, and this we have ln I and ln I0 plus this, which means now I is kind of linearly related to the applied voltage, with the intercept as ln I0 and the slope as this. So for a bipolar junction transistor, it is, as I said, two PN junction connecting to each other. So if there's, and we have this emitter and collector, well, in between we have this base. So if you remember, if there's no applied voltage, gate voltage here, the current, the electrons emitted from the emitter go through the base, and it will not reach the collector because the base is kind of full of holes. So which means the electrons diffused to the base will recombine with the holes there, and there's no current here. To let it have a current, we have to create a kind of channel in the base. How can we do that? It's by having applying voltage here. In this case, we will have a positive applying voltage here, so that the electrons in the base will be attracted to the kind of surface and create a bridge or a channel here, so that the electrons can diffuse over this distance and reach the collector.
You mean apply voltage for B and E?
For base.
Base and
emitter, of course, we have to apply voltage so that we can generate some electrons. But actually, the key point is that we're talking about the base voltage here.
So we need to apply positive voltage.
Yes, in this case. Apply a positive voltage here so that electrons will be attracted to this very thin surface and create a channel.
Thin surface.
And create a channel, if you remember what the Prof. Wang said. And only in this case, electron can diffuse over this long distance. Otherwise, it will be recombined with holes.
So the whole P region is full of positive
holes, yes. But still, it has some electrons. And in this case, it's opposite. We need a negative voltage here to create channels for holes. And of course, the base layer has to be thin because if it's kind of long, we need a very large applied big voltage, which is very not so cost effective and not so easy to control. And the emitter, we have to have it as a heavily doped part, so that enough carriers will be injected. And also the depletion layer of EB, which means the emitter with the base, is kind of narrower than here. This is done by the different doping concentration, of course. And this is how a real BJT looks like. We have this polished side and facing us, and we have this as the base, and 1 and 3 as emitter and collector. And later, Mr. Lin will show you how it looks like. And so the operation of this, as I just said, in this case we have a positive voltage applied, so that the current, the electrons from emitter will go over to the collector and then to the circuit. In this case, this is a closed circuit. We have current here. In this case, it's opposite. We have a negative electrode, so that holes can pass into.
I have a question. Like for the VCC, why is positive is attached to
In this
C?
case,
Yeah. If
because
VCC is a voltage you will collect.
It's
Or
actually
not
the
external applied.
yes. It's actually why it is positive and connecting to the collector is because the carrier here is electrons, if you remember,
Yeah.
and we have to emit electrons from emitter, so
Yes.
which means it has to be connected to the negative side, right?
So we only apply voltage at VBB. VCC is what we get.
No, VCC, of course, we need to
We
apply
also-
voltage so that there will be electrons generated. If there's no
Oh.
voltage, how can we get electrons? This is kind of a switch here, the BJT. In this case, it's like, in other case, it's like we have to close and open the switch only. But in this case, by applying a certain voltage, we can control the open and close status of this circuit.
Can we just apply VBB or just apply VCC?
If we just apply this base voltage, there will be no current at all. So which means, even if the switch is closed, what is the significance if there's no current flowing through?
There will be current if we apply VBB because there's PN junction there.
Yes?
So it will flow from P to N, then come back to the small circle.
Current will not go through here. No, this is not the case. This boundary here, the electrons and holes cannot diffuse through because this is a wire here. The only way that can diffuse through is the PN junction interface. Okay. So for the active mode, the emitter with base interface is kind of a forward biased, and in the collector base is a kind of reverse biased. It is in reverse biased, but it doesn't affect the current here because it is just collecting of the electrons here instead of emitting. So as I just mentioned, the carriers injected from emitter will diffuse through the base because of the presence of this channel here to reach the base collector depletion end and then diffuse into the collector, and then the circuit is kind of closed. If there's no combination at all, which is ideal but never possible, there will be if there's no recombination, the current in emitter will be exactly the same as the current collected here, which means the carriers injected have reached the connector. All of them have reached the connector, and this will result in a very large current flow here in the CB interface. Okay, so for the bipolar junction transistor, we have these 4 characteristics. The first one is the current component. IE equals to, of course, the emitter, base, and this is the collector. So by definition, IE equals to IC plus IP, which means the current generated in the base plus the current collected by the connector. And in most cases, in ideal cases, IB is negligible, so that it can be simplified as IE equals to IC. And for the current gate, we have 2 situations. The first situation is the direct current, and the second one is the alternative current. For the direct current, the current gain is defined as IC over IE, while for the alternative current, it's defined as the change of IC over the change of IE. And it's the same as voltage gain. This voltage gain equals to delta VL over delta VI, where VL is the output voltage, while VI is the input voltage. And this beta function of transistor is talking about the base. So again, the current gain in the base is kind of defined as IC over IB, and in the alternative current is delta IC over delta IB. So talking about this experiment itself, as we said, the objective is to understand the characteristic and then characterize the circuit, and of course then investigate the characteristic as an amplifier. The equipment we have oscilloscope and function generator, digital multimeter, and of course the project breadboard. And the device we have the PN junction diode, this bipolar junction transistor, which we use NPN in this case, and the different capacitors and the resistors. So the circuit assembly will kind of be the tricky part here, but later Mr. Ling will show you step by step how to do it. And then let's have a look at this breadboard, which is quite new to you guys, I think. In this case, we have different blocks in one board. And between different blocks, there's no connection. And between different rows in the same block, there's no connection either. The only case that has this connection is within the same row in the same block. This is the only part that you have to remember. Okay, within the same row in the same block. So for instance, we have point A, B, C, D. If we want to connect B and C, what should we do? We need a wire to connect E and F. And what if, and of course, we can shift the end of B to this point. And in this case, B and C are kind of connected. And what if we want to connect C and D? We have a wire connecting G and H here. So for the report, actually for your group, I think it's a formal report, which means you have to
informal
is it
report.
informal report? So for this informal report, I think it's 1 week due, which means you have to submit within 1 week, and there's no introduction, theory, and equipment. You just answer the question, put on the results and discussion, and the conclusion, of course. And the page is not limited, but try not to make it too long. And there's something you have to take note, which is that you do not copy from the manual. It doesn't help. Just state what you understand. That is enough. And then please don't make it overlong, and no over decoration. Just make it simple. And please, and this, of course, I don't think nobody will do this, but just as a reminder, no handwriting. And the subject will be going through the NTU learning. You'll find a link here. Okay. Okay, this is for formal report only. So the experiment will be conducted by Mr. Lee. And I have to remind you that this is a very lengthy experiment. The two groups previously they did it until 12 o'clock. So I would say that you may want to plan a little bit. You want to divide the duties to different group members and kind of do it simultaneously. Okay. And this is my email address. If you have any questions relating to the report or the experiment itself, just email me. Okay. So now I need you to divide yourself into 3 different groups.